Welcome back, ladies and gentlemen. We're going to be continuing our discussion of organic chemistries by taking a look at hydrocarbon reactions. Why? Well, we started the organic unit and I talked about the fact that we're sort of learning the language of organic chemistry, just like we learned the language of covalent and ionic chemistry. Right? And just like with those two, we started with the alphabet, the periodic table. Then we did the words, chemical formulas. And then we did sentences, chemical reactions. So we've been doing our words, we've been doing our elements, carbon, hydrogen, nitrogen, oxygen. We've done our words, chemical formulas, drawing them, the names for them. Time for sentences. Now, on the plus side, we're not going to go into as much detail on the sentences this time, not compared to what we've been doing on the other times. So don't worry about that too much, okay? We're going to do some basics. And if you really want to know more, don't worry, you'll learn more as you go through chemistry. All right, so here's the first one, an old favorite. It's combustion. We know combustion very, very well. And here we go, combustion of C4H10 with O2. Well, you know it's going to produce carbon dioxide and water, with the exception that when you're in a low oxygen environment, it will produce carbon monoxide instead of carbon dioxide. But most of the time, we're going to be out in the open, so we're going to have lots and lots of oxygen, very little hydrocarbon. So I've dragged this out long enough. Have you figured out the balance yet? Have you worked it out? I hope so, because here's the answer. Ta-da! Couple double bonds drawn here. We can even see a couple lone pairs. Those are electrons that aren't doing anything, basically. Okay, so there we go. That one was a little bit of a tricky one. Moving it on, here's something else that's a little tricky. When hydrogen is replaced with a halogen, we call this halogenation. So a halogen, reminder, is fluorine, chlorine, bromine, iodine. I know that last one breaks the pattern. And what we're dealing with here is that these guys need one electron to be happy. Hydrogen needs one electron to be happy. Hydrogen that is part of an organic molecule is already happy. So it's like, well, I'm good. Everything's fine. I'll be just sitting here. But then say fluorine, the biggest jerk of the periodic table, comes wandering over. And what does fluorine do? Hydrogen, I want your spot. Get out of your seat. And hydrogen isn't going to say no, not to fluorine. Nobody says no to fluorine. So that's what halogenation is. It's where you take something that's already there, you pull it off, and you replace it with a new one. And here's a couple examples, right? Oh, yeah, here we go. Little animation showing it, right? The chlorine comes over, grabs one of the hydrogens. They make their own hydrochloric acid. Off they go. And then the extra chlorine, who's all by himself, is like, well, I'll just take over. Ta-da! We get ourselves a chlorinated component. So there you go. That's the kind of thing that we're dealing with. Now you'll notice, it was a little subtle, but the animation showed a little bit of heat, a little flame that would shoot up just at the beginning. That would be the energy we would need in order to break these guys apart. Cool. Well, that's the idea. Let's try one or two. So we got ethane and Cl2 and pentane and I2. Ooh, I've even got the 2 there telling you already how many there are. Have you figured out what they are yet? I'm delaying. Have you done it? Have you tried it? I hope you did, because here's the answers. First one right there. There it is, written chemical formula style. Let's do it with some pictures. There it is. The HCl, I forgot to draw that. Doesn't matter. You see the basic idea, right? You just simply replace one of the hydrogens with one of the chlorines. It says light under the arrow there. That means that you need to give it energy. That means this would be a endothermic reaction. It needs energy to happen. Pentane, I didn't go getting fancy. I didn't go grab a picture. There's the answer. We see some extra hydroiodide. I'm not sure what HI would be. Iodic acid, maybe? Hydroiodic acid? Yeah, probably hydroiodic acid. There's some of this stuff over here off to the side, but you'll see the main show here. An iodine replaced a hydrogen. They're pretty easy to figure out, broadly speaking. I mean, I had 12 hydrogen. Now I have 11 hydrogen. Where did the extra one go? It's the iodine. All right. These ones are pretty boring. What about this one? Addition reactions. Now, these are starting to get interesting. This opens the alkenes and alkynes at the multi-carbon bond. So we started with, for example, here, an ethene, or an ethylene. That's a weird way to pronounce that, to be honest. And we make a ethane over there. So an ethene becomes an ethane. Pretty straightforward. This is pretty useful, though, because it allows us to turn an unsaturated hydrocarbon into a saturated hydrocarbon. Now, by itself, why do we care? Well, because we can take it a little further. You see, oh, okay, fine. Let's do a few examples first. Give these a shot, right? Heptene, butene, hexene, you know what's going to happen. In this case here, we're going to do some halogenation at the same time as my addition because I'm throwing in some halogens. Here, though, we're just going to use hydrogen like we saw on the previous slide. So here are the answers, or at least the answers that I went with. We got a lot of chlorine getting in there, a lot of bromine getting in there. For the hydrogenation one, not so big. Hydrogenation, he says. Hydrogenation? What's hydrogenation? Ah, that's this. It's addition, but with hydrogen. It happens so often we give it its own name. All right, we've seen this before. So hydrogenation, we know what that is now. But why is that important? Because of this. We've got a big cauldron of oil and a tank of hydrogen gas. This turns unsaturated liquid vegetable oil into saturated solid shortening or margarine. Butter is made from fats, so is oil. The difference is one of them comes from animals, one of them comes from vegetables. Now, vegetables are pretty easy to grow. We can grow tons of it in a field. Animals are a little harder. Sometimes you can get the fat from the animal in advance, like, say, milking them. But most of the time, if you want to get the fat out of the animal, you gotta kill it. And while people do like to eat meat, we like fat too. So it sort of becomes where can we get enough of it? And there's certain things to be said about vegetable oil. But the problem is that why both of these are fats, but vegetable oils are unsaturated, whereas animal fats are saturated. Now, why would we want to make solid shortening or margarine? Certain recipes require it. The different behaviors of the fats allow for different types of chemistry, different kinds of baking. Plus, it's just useful to be able to make these from nothing. Well, not nothing, but from vegetable oil. So why does this whole thing work? Well, saturated fats stack better, right? You're going to see this. These ones here are, well, they're not actually fats, these are acids, but the same idea holds. These will stack much better. We talked about this a few times, right? I can stick these together very easily. These weird bendy ones, all of these in cis arrangement, because that's what most of life is, all of these in cis arrangement, they're going to have a hard time stacking together. And you can see, right? This one here melts at 70 degrees Celsius. This one melts at -5. I'm not sure if you can actually see that. -5, that's not much to go on. So what's going on here? Well, because they stack together better, you can get more intermolecular forces holding the molecule together, right? Little physical properties coming in. So this means that we can make a solid butter quotation marks, from plants, a margarine or a shortening. That's what it is. It's plant oil turned solid. Pretty useful for baking. Cheaper, too, as a result. But there's a downside here. You see, as we learned in stoichiometry with percent yield, not every reaction goes to completion, right? It's never 100%. We always get some fractional percentage. Now, often that just means we'll have some reactants left over, but we could get something else instead. And in the case of hydrogenation, we do. In the case of hydrogenation, some unsaturated fats keep their double bonds. This would be fine, but in order to make this whole thing work, we needed to give it a lot of energy. So it's at a high temperature when we're doing it. What this does is that it temporarily opens the double bonds. So those double bonds that exist to make the whole thing a cis arrangement, they temporarily open, allowing things to rotate before locking in place again. And so we go from being cis to being trans arrangements. Basically, it's kind of like we heat it up and then there's all of this extra hydrogen flying all over the place, but it doesn't quite land on those ones. Those particular ones still move around. They still shuffle around because, as we know, particles move randomly. So when they're moving randomly, they're rotating around. They're going from their cis arrangement to their trans. Then they lock up again. Well, now they can't rotate anymore and they get stuck in the trans form. And as I mentioned the other day, we can't really process trans fat. It's not good for us. I mean, I did a little digging. There is a little bit of trans fat in naturally occurring processes because all chemical reactions are not perfect. But we really can't process trans fats very well. So, Yeah, here we go. A cis fat is supposed to go with being saturated, but instead sometimes it will turn into trans fat. Now, this, when it originally was discovered, was actually considered a good thing because, as I mentioned, most living organisms, well, all living organisms really, they can't handle trans fat. But that includes you or I, but it also includes bacteria. So trans fat wouldn't spoil because bacteria won't eat it. This means you could put it on the shelf for longer. So as far as the food industry was concerned, this was a win-win. You can make this trans fat stuff, it sits on the shelf longer, and as an added bonus, because of its trans character, because it didn't interact very well with human biology, it was sort of smoother. Trans fat is a cheap way to make icing creamy, to make it smoother than it normally would be. But there's a downside to all of this. It's got huge health repercussions. It's terrible for you. These days, we've stopped doing partial hydrogenation of vegetable oils in order to make shortenings and margarines. Now they require it to be 100% complete, which we can test. It just means that you have to do the reaction a lot longer. You've also got to sort of purify out the stuff that was trans. That's the main thing. So basically, before they were like, all right, we're just going to dump in a big vat. We're going to do a whole bunch of it. We're going to take it out. Most of it's cis, but some of it isn't. Generally speaking, no problem. Now they have to be like, all right, we put it in, we take out the part we want to keep, and the rest of it becomes garbage. Less than ideal, but it could be worse. And they could always accumulate enough of the trans fat and then eventually try to rehydrogenate it again. It's just expensive. And, companies don't like expensive, but I prefer the whole not bad for you part. So, yeah, it's not bad. Notice, this is only when you turn vegetable oil into shortening or margarine. By itself, there's no specific problem with vegetable oils, right? The oils themselves, olive oil, canola oil, grapeseed oil, take your pick. All of them still behave the same way, right? It's only the transformation from liquid to solid that causes this trouble. But that said, the next time you're out, you're buying something, maybe from a grocery store or something, check to see. Does it have trans fat in it? Might be, especially if it's very, very creamy and wasn't very expensive. Anyway, that's about it. We're going to leave it there. Next video, we're going to start talking about aromatics, aka smell and taste. Yeah, we're getting right into food. But anyway, see you guys next time.